Okay, so now we're going to take a look at a couple of the chemical properties of the alkenes and the alkynes. And compared to the alkanes, the chemical properties, the chemical characteristics of the alkenes and the alkynes tend to be a little bit more exciting. They're not as bland as the alkanes. And the types of reactions that your alkenes and alkynes are going to undergo are called addition reactions. And the reason why they're called addition reactions, believe it or not, is because things, or we're going to say atoms, can be added. And specifically, they're going to be added to a particular location on the alkene and the alkyne, and that location is or are the carbons of the double or triple bonds. All right, so that's really going to be the center of attraction, or the center of activity when it comes to the reactivity of the alkenes and the alkynes. So in your alkenes and the alkynes, the double bond and the triple bonds are very, very, very reactive, right? And we didn't see this type of reactivity in the alkanes because the alkanes did not contain either double or triple bonds, right? They just contain single bonds, and like we said, their reactivity was kind of very unexciting, which is just a nice way of saying boring. So in terms of the addition reactions, there are three main things that we can add to the alkene or the alkyne, and we name the reactions according to what we're going to be adding to the carbons of the double bond. All right, so again, remember, we're going to add atoms to the carbons, right? This is specifically where the atoms are going to go to the carbons of the double or the triple bond. So what types of atoms are we going to add? We can add hydrogens. And when we add hydrogens, that's called hydrogenation. We can add water, and that's called hydration. We can also add halogens, and that's called halogenation. And each of these reactions are going to occur under special conditions, and there are certain things that are going to be required for them to occur. And we'll take a look at each of these here in a second. So hydrogenation, we're going to be adding hydrogen, so plus hydrogens. So we're going to react the alkene with hydrogen. Reactants, sometimes you'll see the term reagents being used. Reagent just means reacting agent, same thing as reactant. In some cases, we're going to need a catalyst. All right, we talked about catalysts in, I think it was chapter 8. Remember, catalysts are things that speed up. They make the reactions go faster. So in a hydrogenation reaction, we're going to need a metal catalyst like either platinum or nickel or palladium. And if we react an alkene with hydrogen in the presence of any of these catalysts, we end up making the corresponding alkane. All right, so in other words, we end up saturating the molecule, the alkene, with hydrogens by adding more hydrogens to it, as many hydrogens as it can accommodate. Hydration, we're going to be adding water to the alkene. And in this case, we're going to need a catalyst, which is going to be a strong acid. There's a shortcut that we use to represent the acid. We just say H+. Right, if you remember back from chapter 10, acids are things that produce or that give up protons or H+ ions. Right, sometimes you'll see just H+, or sometimes you'll see a strong acid like sulfuric acid. The corresponding product that we get is actually an alcohol. And we'll show you how that happens here in a second. The third reaction that the alkenes, the third type of addition reaction that the alkenes can undergo, and alkynes, is a halogenation. Right, and here we're going to react the alkene plus a halogen, so either chlorine or bromine are the most common ones that we're going to see. No catalyst is needed for this. Right, this actually happens very readily. And we'll show you what the products are going to be here in a second. All right, so we'll take a look at each of these three addition reactions in a little bit more detail. So in hydrogenation, hydrogens are added and again, they're going to go to the carbons of the double bond, right? That's where all the action happens in an alkene or an alkyne. So if we take a look at an alkene over here, right? So there's a double bond. That's where all the action happens. There's our H2 or hydrogen, right? One hydrogen ends up going to one carbon and the other hydrogen goes to the other carbon. Well, you'll notice here that we run into a little problem, right? If we stick another H onto any of these C's, we end up with those carbons having 5 bonds, which is impossible. So in order to rectify that, we have to get rid of a bond to carbon, and what happens is the double bond ends up being converted to a single bond. All right, so we go from a double to a single. So we go from the alkene to the alkane, which is only made up of carbon-carbon single bonds, right? And the other part of the molecule, this could be, 60 carbons long. The other part of the molecule is not going to change. Everything happens at and around, everything happens to the carbons of the double bond, right? That's where all the action happens in your alkenes and your alkynes. All right, so let's see here. It says write an equation for the hydrogenation. All right, so hydrogenation means we're going to add hydrogen of 1 butene using a platinum catalyst. All right, so 1 butene, what does that look like? Well, but, right, that means 4 carbons. E means alkene. And the 1 tells us the double bond starts on carbon 1. All right, so here's 1, 2, 3, 4. There's my but. I have a double bond that starts on carbon 1. There it is, and that's my 1 butene. And we said that we're going to react that with hydrogen, H2, in the presence of a platinum catalyst, and we usually write the catalyst either above or below the arrow. All right, so I'm just going to draw the H2 like this so we can see where they go. One H goes to one carbon of the double bond, the other H goes to the other carbon of the double bond. So we then just simply convert that double to a single, and we end up with the corresponding alkane, 1, 2, 3, 4. And that 4-carbon alkane is butane. Right, so when you hydrogenate an alkene, you end up with the corresponding alkane. Hydrogenation reactions are actually quite common. It is the reaction that is performed to convert your vegetable oils, to convert them to things like margarine and lard, for instance. All right, so you end up going from these things, these vegetable oils that are liquids, right? They have lots of double bonds in them, and you end up making these margarines and other things that are more solid-like, right? So as you convert your double bonds to single bonds, right, you end up making things that look a little bit more stiff or solid, right? And you know, maybe the terms now are going to make a little bit more sense to you, especially when it comes to nutrition. You probably have heard about saturated versus unsaturated fats and oils, right? Well, this is actually what that term or what those terms mean, right? So a saturated fat means that there are only carbon-carbon single bonds, whereas an unsaturated fat is going to contain one or more of these double bonds in it, right? And having more of those double bonds makes it more like a liquid. Having only single bonds makes it more like a solid, right? And when we get to the lipids chapter down the road, we'll actually see why that is the case in terms of the structures of these organic and biochemical compounds. All right, so let's see if we can write the products for the following. So we have here this compound. This looks like a 4-carbon alkene. So let's just name it. It's bute, and there's a double bond in it, so it's butene. And then the double bond here, if I number from the left side, 1, 2, 3, 4, the double bond starts on 2. If I number from the right side, I get 1, 2, 3, 4, so the double bond starts on 2 either way. So this would be 2-butene, right? And this is in contrast to 1-butene that we drew here at the beginning. So the relationship between 1-butene and 2-butene is that they are isomers of each other, right? They have the same chemical formula, but different structures. All right, we're gonna hydrogenate this, right? These are the conditions for hydrogenation. And when you hydrogenate something, you simply convert it from the alkene to the corresponding alkane. So we end up with 1, 2, 3, 4. And that's butane. Similarly, if we hydrogenate, right, these are conditions for hydrogenation. If we hydrogenate this thing, this is cyclopentene, right? So a cycle, 5 carbons with a double bond, right? Both of those H's from the H2 are going to go to the carbons of the double bond, and we end up making the corresponding alkane, which is cyclopentane. All right, the second type of addition reaction that the alkenes can undergo is hydration, right? And this is the reaction of the alkene with water. Remember, water is H2O, right? Which, again, if you remember, looks like this, an O and 2 H's. And the best way to think of water in an organic sense is it's essentially separated into an H and an OH, right? That'll actually tell you how these things are going to be, or how they're going to react. All right, so in a hydration reaction, the alkene reacts with the water in the form of HOH to form a compound known as an alcohol. All right, and this reaction requires a catalyst, and the catalyst that's needed is a strong acid. Typically sulfuric acid is written, or sometimes you'll just see H plus being used instead of the entire formula for the acid. All right, so again, if you have an alkene, it's shown down here, for instance, right? This is our water, H2O, and it's shown as you want to think of it really as H and OH. One H goes to one carbon of the double bond, and the OH goes to the other carbon of the double bond. Right, and again, the double bond goes away, it gets converted to a single bond, and then we have the H and the OH attached to the carbon. That OH there is the defining characteristic of a family of molecules known as alcohols. All right, so for instance, ethene, a 2-carbon alkene, can undergo hydration, and these are the conditions for hydration. An H can go to one carbon, and the OH goes to the other one. The double bond goes away, gets converted to a single bond, and we end up making an alcohol known as ethanol, which is commonly called ethyl alcohol, right? That's the active ingredient in your alcoholic beverages. This is actually one way to make ethanol, but as you probably know, it's made on a larger scale by the fermentation of sugars. All right, so let's apply that idea now, and we'll talk about one other characteristic of the hydration reaction. So it says predict a product of the addition of HOH, and again, think of that as water, to the following alkene, and we have our acid catalyst being represented. Okay, so let's name this alkene. So we got 1, 2, 3, 4. So this would be a butene. The double bond starts on carbon 1, so that's 1-butene. Okay, so we run into a little situation with this particular reaction. So now we have our HOH, right? So the H can go to one of these carbons of the double bond, and the OH is going to go to the other carbon of the double bond. So which carbon are the H and the OH going to go to? Well, there's a rule that we use that says that the hydrogen goes to the carbon that already has the greater number of carbons attached to it, right? This is a rule named after a person. It's called Covnikovs Rule. Right, it's one of the more common rules in organic chemistry, but this is essentially what it says. So this is going to tell us where the H, which carbon the H is going to be moving to, right? So we have two choices. We can either go to this one or to that one. So then we ask ourselves, which carbon already has the greater number of H's attached to it? And that would be the carbon on the right. And that's where the H will go. It will go to the carbon that already has the greater number of H's, which means the OH then is going to go to the other carbon. So all we need to do is to draw what we end up making. All right, so I'm going to draw the product here in the skeletal structure, and as we saw, we have 1, 2, 3, 4 carbons. So 1, 2, 3, 4. All right, we added an H to the carbon on the right, so that is going to have the 3 H's attached to it. We don't typically show the H's in our line structure, but if you have anything other than an H attached to a carbon, you have to show what that is. And now we have that OH attached to the second carbon from the right, so we have to show that OH attached to it. I'm going to move this up here a little bit. 1, 2, 3, 4. So we have our OH attached there. So that rule, that Markovnikov's rule, is going to guide us. It's going to tell us where, and this really applies to when you have bigger and bigger alkenes and alkynes. It's going to guide us in terms of where the H is going to go, which is again is going to tell us by default where the OH is going to go. All right, so that's hydration. And then the last one is called halogenation. This is the third type of addition reaction. All right, and this is the addition of halogens to a double bond, or triple, depending on if you're dealing with an alkyne. Okay, no catalyst is needed. This happens or occurs readily. Okay, and both, we'll just take a look at an example. So if I have an alkene that looks like this, okay, and I react that with a halogen, so let's just choose bromine, for instance, Br2. All right, remember, everything happens around the double bond, right? Specifically, both carbons of the double bond. So if I had my two BRs, BR and another BR, I'm going to do this in a different color. So BR attached to another BR. Okay, one BR is going to go to one carbon of the double bond, and the other BR is going to go to the other one. So if we were to draw the product, right, again, when you add something to an alkene, the double bond goes away. It gets converted to a single bond. And then because now we've added a bromine to the second carbon from the left, we have a bromine attached here. And we have another bromine attached to the neighboring carbon right underneath. Right, so we go from, this is 2-butene, right? We end up with 2,3-dibromo-butane. All right, that's a third type of an addition reaction where we're adding halogens, and typically the most common halogens that we're going to see are either bromine, Br2, or chlorine, Cl2. And both of them, both of the BRs or both of the Cls, are added to the carbons of the double bond, right? So again, the carbons that make up the double or the triple bond, that's where all the action happens in your alkenes and your alkynes.